Hello and welcome to the video series on trigonometric identities, which is going to be pretty much the main focus of the nebulous concept that is Chapter 7. It's going to focus on identities, when things are and when things aren't identities, and that's going to pretty much carry us forward through the entire chapter, really. So what we're going to look at to start us off is going to be what makes an equation identity, when it is, when it isn't, and also what it means and what we can do with them. So, good times abound. First off, what is an identity? Well, an identity is a type of an equation. You see, we have from way back when, an equation is just saying, okay, I have a left-hand expression and a right-hand expression, and no matter how they're written, because they're equal, that means they have the same value. And, well, equations can be right or wrong. They can be true or false. Some always true equations is saying, well, the value of 121 is the same as the value I get when I take 5 plus 6 and multiply that to the difference of 12 minus 11. And that's always true. 121 is always equal to 11 times 11. So that's always true. We can also have equations that are always false. I wrote one right here. You can write quite a few yourself, I'm sure. But 12 minus 6 is never equal to 0. This is genuinely false. 12 minus 6 is equal to 6. Of course, we also have conditionally true equations, which is the focus of a lot of algebra, right? A lot of algebra is finding when is an equation true, or solve for x. And our solutions would tell us here that this equation, 4x minus 17 equaling 3x plus 5, is only true at x equals 22. Everywhere else it's false. So not to say that the other values don't exist, that I can't try them, but it will just produce an equation that is not true. So an identity, then, is a special type of equation where it is always true. So it always has this property here, 5 plus 6 times the 12 minus 1. It's always true, but also it's for all values of any and all variables that would appear in it. So, first of all, an example of what's not an identity. Now, here I have a trigonometric equation. I'm saying, for any value x, take that sine, multiply by 2, take the cosine, multiply by 3, add them together, and that value is equal to 5. Is that true? Is that ever true? And actually, it's going to work out that this equation I have written here is never true. You can take any value for x that you want, and you will never ever have a true equation. I have specifically taken x equals 0 here to see if it's true or not. So 2 sine 0 plus 3 cosine 0, that's going to be just 3, which is certainly not 5. And actually, we can kind of instinctively know this equation is never ever true, because in order for it to be true, remembering that sine and cosine both have a maximum of 1 in their range, this can only be true if sine is 1 and cosine is 1, which means that on the unit circle I'm at 1, 1, which is not actually on the unit circle. So this is never true. On the other hand, though, you can have equations that aren't identities that still sometimes work. For instance, what if this had been 2? 2 sine x plus 3 cosine x equaling 2. That would actually be true at x equal pi over 2. That would have a value that makes this equation true. But it doesn't work, it wouldn't work for every value x. And so to disprove that one, you would have to pick something that other than pi over 2, really, and that would disprove that one. Takeaway is, even when an equation works for some number of values, that doesn't mean it's going to work for all of them. In fact, the way it works with trigonometric equations, knowing that trigonometric functions are periodic, it's going to have, if there's one solution, it's going to have as many as infinitely many, if not more, which is kind of strange sounding, I admit, but there are going to be a lot of solutions if there's any one solution. So just because you guess a lot of numbers that happen to work doesn't guarantee you're going to have an identity. It doesn't guarantee that there is some number that you haven't tried that it's not going to work for. So for instance, let's say I've got this right here. I've got cosine to the 4th of x minus sine to the 4th of x equaling cosine squared of x minus sine squared of x. So I'm taking those differences there. And instinctively, intuitively, we are cautious about this one because, well, there's just no way, right, that I can take some pair of numbers, right, cosine and sine being some pair of numbers on the unit circle, x and y coordinates respectively, and raise those values to the fourth power and take that difference. There's just no way that is going to be the same as I take the same pair of numbers and raise them to the second power and take the difference. There's just no way, right? So, suspecting it's not an identity, I pick some values to make it be false, or at least in the hopes that it will be false. So I tried x equals 0. There's cosine fourth of 0 minus sine of fourth of 0. Well, that's 1 minus 0, which coincidentally is the same I would get for cosine squared minus sine squared. So that one actually works. Okay, well, a little embarrassed by that. Maybe we would try x equal pi over 4, or 45 degrees. Well, the cosine and sine of those are the same, right? It's going to be root 2 over 2 for those. So if I take those same values, raise it to the fourth power, I get a difference of 0, which is the same I would get if I took those self-same numbers and squared them and took the difference. So that's kind of embarrassing. I've now got 2 strikes against me as far as disproving this as an identity is concerned. So angrily, undaunted, I pick some number, some value for x that is not going to be a nice number. I take 16 degrees. With that, I am guaranteed to not have any symmetries, any reflections, any niceness to work out. And so also recognizing that 16 degrees is an ugly number as far as finding the values of sine and cosine are concerned off the unit circle, I just look it up, I compute them. Sine and cosine come out to be some weird things, and when I raise them to the fourth powers and to the second powers respectively, take those differences, I actually get more or less the same number. And so, maybe now I'm starting to change my mind. Actually, I am. Because now that it's worked for nice numbers and it's worked for ugly numbers, maybe it actually is true. This truly is an identity. Well, I'm not done. All I've done was show it happened to work for 3 numbers. There's infinitely many more I would have to try before I can conclusively say it works for all numbers. And I don't have that kind of time. So instead, recognizing that the statement, I can't disprove it, is not an acceptable reason of saying why you've proved it, let's try something else. And that something else is to start with the left-hand side, cosine of the fourth minus sine of the fourth, recognize that's a difference of squares, right? That's cosine squared, squared, and sine squared, squared. So I factor that using some algebra techniques that we have. I've got cosine squared plus sine squared, and cosine squared minus sine squared. And then recognizing by the Pythagorean identity, right, sine squared plus cosine squared equals 1, that's always true. By virtue of being on the unit circle, remember your unit circle approach there, we've got 1 times cosine squared minus sine squared, which is the right-hand side. This actually is an identity, and we've now definitively shown it. This is an identity. It's always true. And the value for that is simply this. Well, there's more too, also later, but simply, if you ever see, at any point, cosine of the fourth minus sine of the fourth, that reduces down. That always reduces down to be exactly equal to what you would have gotten with cosine squared minus sine squared. So that reduces some of the computations you would have to do. That's nice. And we'll actually get to even nicer ones down the road. So here we are. We know what an identity is, and we're able to show when it's not an identity. Your author likes to pretend this is simple, or easy even. And I would say it is simple because, well, you just guess a number that makes it not work. But it's not easy because there's plenty of numbers for which it might work, your equation. So going forward, we're going to see how to prove an equation as identities, and also where they come into play and what we'll be doing going forward. So see you then.